Okay, there is this nice paper that came out that talks about a new battery they've designed. It's called Polypeptide Organic Radical Battery. We'll just read the summary because it's a lot of chemistry, and I'm not really that good at chemistry, and you have to read the paper yourself. But the idea is good enough that I wanted to just provide a few minutes of introduction to it. Essentially, lithium-ion batteries have revolutionized the electrification industry and everything we use, like phones and whatever else. But obviously, there are lots of issues involved with mining for lithium and cobalt, recycling these batteries, and all sorts of environmental issues in a life cycle sense as well. So you're always hoping to find alternate ways of doing these where you have things that are natural and degrade as easily without causing serious piling up of material that we convert from natural resources into irreversibly into junk, like unrecyclable products. So in that sense, I just wanted to leave this here. We have designed a metal-free all polypeptide organic radical battery comprising redox active amino acid macromolecules that degrade on demand. Okay, polypeptides are basically chains of amino acids, so they are organic, and the redox is basically where there is an electron donor and an acceptor, so that they can do the battery functioning, where you obviously want electrons flowing from the cathode to the anode and then be reformed and so on. And if it degrades on demand, obviously you have a very environmentally safe product as well. This concept represents a first step towards sustainable, recyclable batteries and minimizing global dependence on strategic metals. Viologen, which is another chemical, and by Tempo polypeptide anodes and cathodes respectively, were synthesized via ring opening polymerization of highly reactive cyclic N-carboxy anhydrides. So these are all chemical things used to synthesize the anode and cathode in terms of polypeptides, followed by sequential post-polymerization modifications to incorporate the redox active groups. So you want things that are basically going to change the oxidation state of the substrate as they begin to function. The polypeptide battery reached a maximum charge capacity of 37.8 milliampere hour per gram of mass, with theoretical capacity of 44.5 milliampere hour per gram. So you know how the energy unit works, ampere hour, kilowatt hour, and so on. I mean, you cannot really compare amperes and watts, so you have to be careful. The active components degraded on demand in the presence of acid to generate starting amino acids and other building blocks. Looking forwards, the main challenges are preventing dissolution of the active material and boosting the overall cell capacity. Future studies should focus on preventing dissolution of polypeptides by cross-linking, by post-processing modification, this is a reference 45, or by taking advantage of the solubility of polypeptides in flow battery cells. Okay, technical details of where it can go in the future, but as an experiment, this is how it works. Polypeptide based organic radical battery. So you have the cathode and the anode, and you have the current collector, so you have electrons in the charging and discharging phase produced, going through this place where you want the power, and then back to the anode, and you have the exchange back in terms of continuing the functioning of the battery through the polypeptides. Viologens are on the receptor side and the donor side. Okay, so schematics of polypeptide based organic radical battery and the reactions that occur during charging and discharging are shown on the left and right respectively. The redox reactions for the Tempo and Viologen pendant groups are shown in the middle. For example, during For example, during charging, nitroxide radical functional groups at the cathode oxidize to oxoammonium cations and halogen functional groups at the anode to reduce to their neutral forms. Okay, so these are the reactions here, which obviously I'm not going to explain fully here, unfortunately, beyond my capabilities, but you get the concept. So in the charging stage, that's what is happening. In the discharging phase, you have electrons going from the anode towards the use place, and then the other cable is going to bring it back to the current collector. So you have this kind of standard battery operation, except everything is being run. The donor and acceptor of electron radical generation, everything is organic, based on polypeptides and halogens. So this is the reaction. I won't go again into the details. So you have the halogen on this side, and you have amino acid modification, monomer synthesis, polymerization. So the process is involved along the way, and you have activation and installation, and on this side also you have installation and activation. So recharge, discharge, as we looked at. Lots of detailed reactions here, which go through synthesis of halogen polypeptides, synthesis of tempo polypeptide, and so on. So obviously it's a very brief one, so you have to just follow up the paper to get more details, but it's an alternative solution that's being sought and is demonstrated to work. And obviously scaling up and producing at mass scale has probably a long way to go, but you can follow up the discussion if you're interested in this direction. Okay.